Hello and welcome to the InfoQ podcast. My name is Wes Rice and I'm your host. In addition to hosting the InfoQ podcast, I chair a set of software conferences called QCon. These podcasts are glimpses into some of the people who speak at QCon and other influencers in software. The next conference is in San Francisco, November 5th through 7th. Today's podcast is with Mike Lee Williams. Mike Lee Williams is a research engineer at Cloudera. He works in the Fast Forward Labs team. A little over a year ago, Fast Forward Labs was a separate company. Now it's part of Cloudera's internal machine learning group. Some of the stuff that he's been doing over the last year or so has been machine learning interpretability, probabilistic programming, and federated learning, which we'll talk just briefly about. On today's podcast, we're going to dive deep into the field of probabilistic programming. Probabilistic programming is a family of programming languages that make statistical problems easier to describe and solve. Using Bayesian Inference, these tools take a prior and posterior knowledge feedback cycle to make a prediction and then carry with that prediction a degree or a measure of uncertainty. Today, Mike will dive deeper into how Bayesian Inference works. He'll talk about probabilistic programming. He'll talk about the use cases of probabilistic programming, including things like A/B testing. And he'll dive into some real-world production-ready implementation tools like PyMC3 and Stan, along with implementations from Facebook called Profit that wrap libraries like Stan. He'll talk about tools like TensorFlow predictions and where the industry is going. If you've ever wondered about probabilistic programming, if you've ever wanted to know what it really is and cut straight through the hype, this is the podcast for you. As always, thank you for bringing us along with you, and we hope you enjoy the podcast. Mike, welcome to the InfoQ podcast.
Hi, Wes. Thank you very much for having me.
So before we jump into the meat of this, there's one question I got to ask you. How does a PhD in astrophysics become a Cloudera machine learning researcher?
Yeah, so I did my PhD in astrophysics too many years ago now, more than I like to admit. Turns out that astrophysics these days is a very good preparation for a career in data science and machine learning, and that's for two reasons. One is, there are an awful lot of stars out there. It turns out it's a true big data problem in a lot of settings. And the other reason it's relevant preparation is the data tends to be pretty crappy. Like, there are problems with the data all the time. And to that extent, it kind of matches what we see in tech. Large amounts of data with various problems, and you're trying to draw conclusions from it that allow you to take actions. In the case of astronomy, the action obviously is publish or perish. And, in the real world, it's hopefully something a bit more practical. But it turns out the preparation is appropriate. The downside of that astronomy preparation, I think this is true of a lot of data scientists now, is many of us don't have a formal CS background. We're self-taught coders. We maybe don't even know what big O notation is. And that is a constraint and something that I've personally worked on in my own skill set. And that's, one of the downsides and one of the reasons why there is some challenge in migrating from a field like astrophysics to what I do now.
But even in CS, I think there's so many people, they feel like there's gaps that they have because you can't know everything. But I find that really interesting about astrophysics. Like I read papers sometimes or different things that talk about, like, you're looking for the gaps in data to be able to find something that should be there, but it's not.
Yeah, my PhD was literally that. It was measuring how much matter is missing in galaxies. So I used to say what I was doing was just saying very accurately how big the hole was. Much cleverer people tried to fill in the hole, particle physicists and theoretical physicists. All my job was to do is how much stuff do you need to fill in this hole? It was fun stuff.
Before we jump into probabilistic programming, you mentioned as we were talking, kind of setting up for the podcast, that you've been working on federated learning. It's not a phrase I'm familiar with. Before we jump into probabilistic programming, what is federated learning?
Yeah, so what Fast Forward Labs does is 4 times a year or so, we publish a report on a new idea in machine learning that we think is of interest to our clients who are subscribers to that research. And federated learning is the thing we're working on right now. It'll be the next report. What it is imagine you're training a machine learning model on an edge device, like a mobile phone. So a phone produces the training data. And the traditional way of handling this is to ship the training data back to some centralized supercomputer somewhere from all these mobile phones, all these users of Android or iPhone or whatever, shipping the data back. And then we can train a lovely predictive model. The problem with that is that most people are a little uncomfortable with that idea. If it's your baby photos or, fundamentally it's a keylogger, if it's everything you've typed, that kind of setup makes some people uncomfortable. And in certain legal environments, it's just not allowed. So healthcare, things like that. And then, of course, we've all got data plans with finite amounts of data. So we don't necessarily want to ship everything we do back to some central server over our 4G connection. So this is where federated learning comes in. And the rough idea is, each of us, you, me, and all other users of these phones, train little local models that are frankly not very good because the amount of training data an individual provides is not that huge. But what happens then is instead of shipping back the training data, you ship back the model. The model is a much smaller amount of data. And of course, additionally, it is not the data. It's not the most privacy sensitive thing. There are ways of, given a model, figuring out what kind of training data went into it, but it's a much harder job. And in fact, you can provide differential privacy-like guarantees in some situations about that being impossible. So anyway, we ship these models back, and then the central authority, its job is to literally take the average of the models, and that becomes the global model that captures all of our training data that we've all provided in a privacy-preserving way. So we preserve data locality and privacy, which has like huge implications for obviously consumer tech and healthcare, but also all sorts of industrial applications where the amount of training data generated is very large, and potentially, in remote locations where the internet connection isn't that great or that stable. So it's a very, very wide-ranging thing. We're just getting going on it, and we're really excited about it.
Yeah, that's really incredible, particularly with all the libraries that are now coming out on iOS and Android. Makes it certainly approachable for folks as well.
Yeah, exactly.
All right. So this podcast, while it sounds like we need to do one on federated learning in the very near future, this podcast is mostly going to be focused on probabilistic programming. So let's start off. What is this idea of probabilistic programming?
So probabilistic programming is a programming paradigm in the same way that object-oriented programming or functional programming or whatever your favorite paradigm is a programming paradigm. And that's to say it's a family of programming languages that make a certain kind of problem easier to describe and solve. And the problem that probabilistic programming languages are focused on is statistical problems, analyzing data and drawing conclusions from data. And the reason that is difficult in general, and the reason why a programming language that makes that a more natural and easy thing to do is valuable, is that all data is flawed in some way. Any kind of analysis, the conclusions you draw are uncertain because the data is flawed. You might not have all the data. You don't run your A/B test until the end of time. You run it for a week. Or you might have data that is dubious in some other way. So, for example, you're measuring a physical system like the speed of a car. You measure it, but you don't measure it to the nearest centimeter per second. If you're lucky, you get it right to within a mile an hour. So that uncertainty manifests itself as uncertain conclusions, and we'd like to know how uncertain our conclusions are. And at a high level, what probabilistic programming does is provide a more user-friendly way to answer questions like that based on real-world data.
More is something along the lines of like you make an assertion that it's like an A/B test. It will be used so many, I think in the talk that you did, you said this particular A/B test, one had 6, one had 5% of people converted in some type of sales or something that you're doing. So you make an assertion that 60% of the time users will be able to convert. Is that accurate?
Yeah. If you run an A/B test, you might find that users convert for layout A 4% of the time and layout B 5% of the time. And in which case, well, obviously layout B is better. We're done here. But if it turns out the A/B test was very, very small, so 5% of visitors converted on layout B, but there were actually only 100 visitors, then suddenly you're hopefully less certain that layout B is better. You'd like some more data. And what probabilistic programming gives you is an answer to the question, how uncertain are you? That's a number you can take to your CFO or your CTO or your chief product officer, I guess, in this case, and say, is this certain enough to make a business decision? Do I want to bet $1 million if the odds of me losing that money are 20%? No, I probably want to get some more data until the odds of me being wrong are only 1%. That's the rough idea. It's important to note, I think, that probabilistic programming is a family of programming languages, but the thing we're actually doing when we do probabilistic programming is Bayesian Inference, which is a 250, 300-year-old algorithm that we should probably talk about some more.
So let's do that. Bayesian Inference. That's a big part of what we're talking about. So what does that mean?
The Reverend Bayes, many hundreds of years ago, came up with the idea of Bayes' rule, which is by the standards of statistical equations, a relatively simple one. It's an equation that relates the thing you know before you conduct an experiment and the results of the experiment to what you know after the experiment. So, for example, let's say with the A/B test, let's say one of these website layouts. I have a strong belief that the conversion fraction of this website layout is about 5%, plus or minus 2 or 3%. I'm not certain. If I was certain, I wouldn't need to do the experiment, but I think it's 5 plus or minus 2 or 3. And then I get some data. And the data is, maybe at a high level, roughly consistent with my beliefs, but my beliefs necessarily change in the light of that data. And Bayesian inference is a set of machinery for taking my beliefs before the experiment, and mathematicians and statisticians will call those your prior beliefs, and turning them into beliefs after the experiments, which the nerds will call your posterior beliefs about the world. So that probably seemed kind of abstract and high level, but really what it is a tool for turning what you know before the experiment and the results of the experiment into answers to concrete questions about what to do next and what your data is telling you. The equation is really simple. Unfortunately, as a practical matter, its implementation in code can be quite tricky. And there are a number of reasons that we can have a go at getting into on the podcast, but they're easier to explain with visuals. What those all imply is that for mortals like you and me, as recently as a couple of years ago, it was quite a difficult approach for interestingly sized problems. The Reverend Bayes many hundreds of years ago used it to solve toy problems. And in my talk at KubeCon, I used it to solve toy problems, but real internet scale problems, by which I mean large amounts of data and large numbers of parameters being things you don't know, are very difficult computationally to solve with Bayesian inference. Probabilistic programming is exciting because it abstracts away a huge amount of that complexity and makes this sort of gold standard technique accessible to less sophisticated statisticians. If the last time you took stats was high school, don't stop listening now. This approach, in my view, is accessible to non-professional statisticians.
We'll jump into some of the different tools that you can use today to be able to apply this in just a second. But to go back to this can be a very iterative approach, right? You can create these beliefs, these models, have this data coming in. You have this Bayesian inference that's going on. You have a revised, this posterior distribution that comes out of it. And then that can feed back in to the prior distribution, which then becomes this kind of iterative process that continually gets you to a better posterior of distribution, right?
That's right. It's a really virtuous circle. If you're in a sort of a streaming environment where new data is arriving every day, you don't have to wait until you've gathered a week's data to see results. You can run this analysis effectively, not just effectively, literally a streaming setting. As each piece of data arrives, your prior is updated into a posterior distribution, what you now know given that data. And that posterior distribution becomes the prior for the next piece of data. And so that means the posterior at the end of this sequence of data is available to you throughout the stream as like a live picture of your knowledge of the world, which is a really exciting possibility. I mean, in an A/B test, live how well layout A and layout B is doing, and you can end that test early if it's obvious one is better than the other. Perhaps most acutely and famously, this analysis is done during drug trials because you want a live picture of, is the drug working or is it killing people? You don't want to wait until the end of the trial to find out 3 people have died, and that is statistically more than you'd expect. You want a live picture that allows you to end a trial as soon as you know the drug is effective or dangerous. And obviously, most of us don't deal with that kind of life and death, but that's the advantage, I think.
This is some way that you can build a predictive pipeline, right? I mean, it started off where we had batch, and then we went to real time where we had the streaming data where things were air quotes real time. It could have been a minute, 5 minutes, an hour ago. But with the tools you're talking about with like Bayesian inference, you can actually get to predictive analytics to where you're actually saying what's happening right now based on kind of the predictions that this model may be giving us, and even kind of slide the timeline forward to be able to look at what may be happening in the future. This is what tools like this can give you, right?
That's right. It's a beautifully coherent way of looking at things because it does work in the batch setting. You can give me 1 million data points and I can run my batch Bayesian analysis on it and tell you whether layout A or layout B is better or whatever. And we can go and make a business decision based on that. Or I can say, instead of giving me 1 million, give me 1,000 at a time, or give me a day's results at a time. And we can have this sort of result that lags with a day's latency, but is still, in some sense better than the batch result. Or we can go truly streaming and keep this posterior distribution up to date live as each visitor arrives. And obviously, there are engineering practicalities associated with that last approach. But all three of those approaches, like the truly batched, like the semi-batched, if you want to say it like that, and then the streaming approach, all three of them under the hood are using Bayes' rule. All three of them are using the same approach. So in a sense, it's a difference of degrees, not a truly qualitatively new system, algorithmically at least, to migrate from your traditional batch analysis to the gold standard streaming analysis. And as you say, the really exciting possibility is being able to forecast about the future. And I don't want to suggest that, Bayesian inference is the only way of doing that, or probabilistic programming is the only way of doing it. Like supervised machine learning in general, almost by definition, is capable of doing that. What I think is really valuable about the Bayesian approach to supervised machine learning is that predictions come with measures of uncertainty. So remember I said we're doing this A/B test and we're trying to say layout A or layout B, and we want to know how certain we are. You can imagine making a prediction about a number, how many dollars am I going to make tomorrow or in a month's time or whatever. And that number, the dollar amount, is useful, but what's at least as useful is a measure of how certain I am about that. Do I think I'm going to make $1 million plus or minus $1, or $1 million plus or minus $100,000, or even plus 100,000 and minus 500,000? Those have very different implications for how your CFO should plan and how much cash she should have in the bank.
You can measure risk, right?
Exactly. You can quantify risk. And in financial situations, obviously, that's acutely relevant, but all sorts of situations where you're planning for the future, you need resources in proportion to how often you expect something to happen. Being able to predict how often something is going to happen and how uncertain you are makes your ability to prepare that much richer and more rigorous.
So we obviously can't go into any of the Python or any of the code to actually talk through some of this stuff, but I just want to point out on the podcast that you have a presentation that you did that we've referenced a couple of times at QCon New York in June that kind of walks through some of the implementations, and you'll go through kind of a brute force, kind of simple, fairly simple Python examples that just uses a for loop that does a brute force implementation to show kind of at toy scale how you can do some Bayesian inference and be able to use probabilistic programming. But I think the more interesting part for the people listening are some of the tooling that provide abstractions that are out there that offer things like Metropolis Hastings and Hamilton Monte Carlo with automatic differentiation and no U-turn sampler, to be able to apply these abstractions so that you don't necessarily have to understand the automatic differentiation aspect of Hamilton Monte Carlo to be able to apply some of this stuff. So can you talk about some of the abstractions, the tooling that's out there around Python and R that allow you to be able to implement some of these things without having a PhD in statistics?
Yeah, so the approach I took in my talk was trying to build a probabilistic programming system from scratch, which in many ways is a completely insane thing to do. I think it has pedagogic value, but don't watch my talk expecting to copy the code and ship it into production. One of the things you get when you do build a probabilistic programming system from scratch is a big appreciation for how slow it can be if you're not very clever. And it turns out that in order to be very clever, you need essentially a graduate degree in statistics. A number of fairly deep mathematical problems were solved in the last sort of 20 years or 2 years, depending on how you count. And those solutions are what we call robust. They mean that the user of the algorithm does not need to tune it for each individual problem. The solution is pretty idiot-proof in a lot of ways and is not something that is going to be fragile against tiny little changes in the setup of your problem. And I think the most robust algorithm, the algorithm that is used the most today, it's perhaps already not the most cutting edge. This is a fast-moving field, but the most robust algorithm for right now is Hamiltonian Monte Carlo with automatic differentiation and the no U-turn sampler. And it's harder to code than it is to say, and it's pretty difficult to say, that algorithm. It's a very deep and complicated algorithm. It turns out, my background in astrophysics is surprisingly relevant to that algorithm. It shares a lot in common with orbital mechanics, figuring out what the solar system is doing and stuff like that. So you already, hopefully, you're breaking out in hives about how sophisticated the maths here. All this is building up to saying the wonderful thing about probabilistic programming languages is those algorithms, to an extent, become one-liners. It's your job to set up the data and describe your problem, but you essentially push the Hamiltonian Monte Carlo button and out pops the posterior distribution. That at least is the goal. In practice, it can be harder or easier for some problems than others, but it really is, in terms of the code, a one-liner. So that's one of the two big things probabilistic programming systems do, is have industrial strength, very fast implementations of algorithms that would otherwise be tremendously difficult for most people to implement. The other thing they do is define as like a primitive data type the objects we think about when we do probabilistic programming. So imagine, if you're building a GUI toolkit library, you're going to define primitives like, window and the close button and dialog box and things like that. Probabilistic programming languages do the same thing. They provide a library of primitives relevant to these kinds of problems. In particular, random variables and probability distributions. Those are off the shelf, available to you, nice, fast, well-designed implementations that you can compose together to describe your problem. And the problem description you end up writing in these languages ends up being very declarative, by which I mean you don't find yourself writing a lot of for loops and thinking about the order in which things need to happen. You simply describe the world and push go, and the probabilistic programming language figures out the implications of that. That at least is the goal. There's devil in the detail, but that at a high level is what these languages try to do.
What are some of the languages that are out there that are being used in practical real-world settings, not just academic languages?
Yes. If you have a practical real-world problem today, there are two languages I'd recommend you take a look at, Stan and PyMC3. Both of them are appropriate and fast enough to solve big, big problems. They are relatively mature languages with great documentation. PyMC3, as you may have guessed from the name, is like a superset or a library that you use it from within Python. And in that sense, PyMC3 is probably the more user-friendly of the two for most people listening to this podcast. On the back end, it's actually using a library called Torch, which if you've done any deep learning, you may have heard of. It's a now end-of-life 1.0 deep learning library. And what it's using that for is to do auto-differentiation, the automatic differentiation bit of Hamiltonian Monte Carlo. The PyMC3 people didn't implement that themselves. They just used the deep learning library. So this is not deep learning, what we're talking about today, but it has very strong, both at a high level and low level, overlaps with that very exciting field of machine learning. So PyMC3 is going to do all these things. It's got this fast implementation of algorithms like Hamiltonian Monte Carlo and other algorithms that may be more appropriate in other situations. And PyMC3 is pretty smart about figuring out which of those algorithms to use, in addition to doing a good job of implementing them. And then it's got these random variable and distribution primitives. And you write code that looks, it is Python. It's syntax compatible with Python. It looks a little unusual, but fundamentally, you are describing a problem, and then you press go. And that's what the experience is like. And of course, because you're using Python, a general purpose programming language, that raises the possibility that you can wire this application into, for example, a web server. And then you've got an API that serves out samples from the posterior distribution or the answers to statistical questions over a web API. So your friends on the front end can talk to your back end because you have this probabilistic programming language that is essentially a dialect of a general purpose programming language. So that's the place I'd start.
You also mentioned Stan. What are its strengths?
Stan historically has had the fastest implementations of all these libraries, and I think that's probably still true, perhaps a little less true than it used to be. Stan is academic code that is used in production. It is used particularly in the pharmaceutical industry, in drug trials, and sort of environmental sciences, in sort of industrial applications. In terms of the way most production software engineers think, it's a slightly unusual language, I would say. The documentation is voluminous as well as good. So, you are biting off quite a lot. That said, the community around Stan is incredible. The mailing list is amazing. So even if you've got a PyMC3 question, if you can translate it to Stan, ask it on the Stan mailing list and you'll get a great response. So they're both worth checking out.
I think you also mentioned in your talk that there's an abstraction that Facebook has created, Profit, that actually encapsulates Stan. Is that right?
That's right, yeah. So Stan is a general purpose programming language in the sense that in a formal CS sense, it is Turing complete. But you probably wouldn't use it to solve general problems. But it is very flexible. And that flexibility is, for some use cases, a disadvantage. If you have a very specific problem you want to solve and you want to make the solution accessible to, let's say, data analysts or data scientists, less sophisticated coders, then what you might do is encapsulate a specific Stan program with some plumbing to allow it to connect into languages that data scientists are familiar with, like R and Python. And that's exactly what the Facebook data science team did when they built Profit. Prophet is a general purpose time series forecasting library. So you feed in a time series and it predicts the future, basically. And it captures any seasonality in the time series, by which I mean, if you get more visitors to your website Monday through Friday than you do at the weekend, Stan is going to capture that. It also captures seasonality at lower levels and higher levels, not just days of the week. And then crucially, its forecast incorporates that seasonality and incorporates uncertainties, bounds on what can happen in the future that are implied by your data. The longer the archive of data you have in general, the more confident your prediction about the future will be if you use Prophet. If you have a very short archive of data, Prophet will still make a prediction. It won't throw its hands up and say, I give up. But that prediction will be correspondingly uncertain, and that is a piece of information you can use in itself. And because of very good essentially UX decisions the Prophet developers have made about how the model works and how it talks to Python and R, this is I think a particularly accessible place for most people to start. You really can be up and running in 4 or 5 lines of code and looking at the real output of Bayesian inference, namely the posterior distribution, without necessarily opening up the, frankly, rather messy black box that is Bayesian inference.
Yeah, it's super impressive. Given time series data, being able to take streaming data and then make future projections with it, I think that's incredible to be able to do forecasting use cases.
Exactly. It's a generic problem. Most of us have some kind of time series data. And I'm a machine learning person with a background in time series, and I find time series generally pretty tricky to work with. There's a reason why the hello worlds of machine learning are things like classifying orchids and people who died on the Titanic and stuff. These are the standard hello world data sets. They're very simple tabular data sets. Time series are not like that. They can be arbitrarily long. They have all sorts of long-range dependencies, which is a fancy way of saying they're periodic on different timescales. They can be a nightmare to really analyze, and yet they are so common. So that's one of the reasons why I'm very, very excited about Prophet.
So that's forecasting. But one of the things that I wanted to kind of also hit on, and I'm kind of just throwing this one at you, so forgive me, but basically what I'm curious about is your thoughts on how these data structures around probabilistic programming and Bayesian inference, how they're going to affect kind of like our core programming languages. And what I mean by that is we have huge and just ever-growing amounts of data. And you talked about the idea of declarative programming. We can't just iterate over every single piece of data that's coming in anymore. So it seems like that there is a place for these data structures, these primitives that we use in our core software programming languages that need to take into account the concepts that we're talking about with probabilistic programming. Where are languages going? Where do you see languages going?
That's a really, really interesting question. It hits on a couple of things I'm pretty excited about. The first is probabilistic data structures. And if you have a CS background, you probably know what a
Bloom filter.
Yeah. And you can imagine Bloom filters or things like Bloom filters being incorporated at the language level. And if you're interested in Bloom filters, check out cuckoo filters. They're kind of the new hotness in the Bloom filter world. You can delete entries from cuckoo filters, which is famously not trivial in a vanilla Bloom filter. That kind of analysis at the programming language level is a very useful affordance in this world that, as you rightly say, we now live in which data is coming in at such a rate that we can't store it, we can't persist it, we can't hold it all in memory to do some batch analysis on it. We may not even be able to move it over to the network to a more powerful computer that can do that because it's just too much. So at the language level, you can imagine that stuff becoming more and more useful. The one place in which I've seen Bayesian inference incorporated almost at the language level is an MIT project, and I know your head is sinking now because I'm talking about academic research projects, but I think this one is particularly interesting, called BayesDB. BayesDB is essentially a superset of SQL that allows you to do, selects and filters and all those sorts of SQL things. But the really nice thing is it allows you to impute missing data and select on a criteria that is missing, and the gaps are filled in a probabilistic way. And so it adds to SQL's set of primitives an infer statement that infers missing values. And under the hood, it's using Bayesian inference. But from the point of view of the user, it's just another primitive in the language. That code is public. You could use it, especially for people on the database side of things who deal with missing data and think about how can I make potentially quite complicated algorithms more accessible to general users. I think BayesDB is really interesting.
I remember a talk that was by Jawbone. So Jawbone is that health meter that you wear on your wrist that tracks kind of health data. But people also go to sleep. People take it off, so it misses data. Remember that Bayesian Inference was being able to use to be able to fill in that missing gaps in the data. That was another interesting use.
Yeah.
I want to touch a bit on something that we talked about before we actually started recording. So we talked about PyMC3, and it's based on an earlier version of Torch. There's a follow-on version, right? That's PyMC4, I believe, and it's based on TensorFlow probability. What can you tell us about this relationship?
That's right.
Not replacing it, but creating it, kind of an abstraction.
Yeah, PyMC3 on the back end is using this deep learning library Torch that, for various reasons is not going to see any further development. So the PyMC team had a problem, but they also had an opportunity. And they've decided to shift their back end over to a new back end, TensorFlow probability. And as you can guess from the name, it's a Google project, which I think speaks to, an organization like Google throwing weight behind this movement, I think is very, very exciting. TensorFlow probability, I don't immediately necessarily recommend you go out and install it. It's a fairly low-level set of tools that is, from my point of view, to the extent I understand it, geared toward people developing probabilistic programming languages or doing very innovative researchy analysis. And to that extent, you can think of PyMC4, which is the PyMC version that will be built on top of TensorFlow probability, as a user-level implementation of probabilistic programming that uses TensorFlow probability as the back end. So this is kind of similar in the same way when people ask me, I want to learn deep learning, where should I start? I, in general, don't recommend starting with TensorFlow because it is a relatively low-level library. There are libraries that abstract away some of the complexity and provide building blocks of neural networks, things like Keras, on top of that are a little more user-friendly and allow you to focus on the problem and the algorithms rather than the nuts and bolts. TensorFlow probability is kind of the same deal. Like, identify a library that sits on top of it rather than necessarily bang your head against the wall with that for now. If this is the first time you're hearing about probabilistic programming, if everything we've said today is old news to you, by all means, check out TensorFlow probability. It's very cool to work.
When you say TensorFlow probability, from your understanding, that TensorFlow is more of the brand name. It's not a new package for TensorFlow that's based on probability.
That's right. That's my understanding. It's kind of like if you go on GitHub and look at the TensorFlow organization, there are lots and lots of packages, including TensorFlow, the deep learning library. And not all of these packages are immediately directly related to one another. So I think TensorFlow probability falls under an umbrella.
All right. So if you enjoyed this podcast, look for Mike's videos and presentations. You can find them all online. I recommend the ones that he did at QCon or QCon AI. In addition, check out blog.fastforwardlabs.com. That is one of my new favorite resources that I pay attention to for machine learning data science sources. There's all kinds of great blogs. There's all kinds of great walkthroughs on things like PyTorch, on using Three.js for data visualization. Machine learning interpretability, that's another area that Mike has done a lot of talks at QCon talking about how to really understand how a neural network got to a decision. So machine learning interpretability is one of the things you can find on there, and a whole lot more. Mike, as always, it's such a pleasure to talk to you. Thanks for joining us on the InfoQ podcast.
Thank you very much, Wes. It was a pleasure.